Hi, I'm Jayeon, and our team members are Chaerin, JunHoo, and Jooeun. We studied category-aware and scale-aware unsupervised domain-adaptive object detection. First, let's look at the problem setting for UDA. In the problem setting of UDA, there are two similar but different domains, source and target, and our goal is to training object detector to adapt well on target domain with labeled source domain data and unlabeled target data. Before entering the method, let's see the motivation of our method. The figures are t-SNE of backbone features of FCOS, and A is the feature distribution according to the object category. Different color means different categories. And in B is the feature distribution according to the width of the GTP boxes, and C is the distribution according to the width of the B boxes of only car objects. The darker the color, the larger the width of GTP boxes. And in C, it is more clear that the distribution varies according to the scale. We use FCOS as our object detector, and FCOS is one-stage detector that predicts not only classification and B-box regression values, but centeredness score on every location of the feature maps. It is the overview of our method, and we used the adversarial training scheme commonly used in DA. The discriminator here is trained to distinguish the domain of features, source or target, and backbone is trained to generate domain invariant features. However, we are not trying to align the overall features, but to align the features in a category-aware and object scale-aware by using classification predictions and B-box regression values. There is a study in 2018 that performs domain adaptive classification by conditioning features through outer products, and we took the method and applied it to detection. Let's see category feature alignment in detail. To focus on foreground objects and get content prediction, we generate masks using classification probability and centeredness probability. And then we can get category-aware feature by the outer product features and classification probability. In the case of statistics, the dimension of condition features would be by 256. And at the beginning of training, since the classification prediction is not accurate, we start with a vector 1 over n with uniform probability for all classes and gradually increase the ratio of prediction. So we can get condition features and fit a category feature to the discriminator to align the distribution in a category-aware manner. We applied similar methods to scale-aware feature aligning. However, regression values left, top, right, and bottom is continuous, not categorical. So we need to convert the regression values into categorical form. So we simply bin the continuous regression value into 3 classes, like in equation 4. We determine the binning threshold heuristically based on distribution of object scales in the data sets as shown in left figure. So we grouped the regression value left and top into 3 bins respectively. So we can get also scale-aware features by outer product of features and one-hot vector of regression prediction, and then feed the condition features into the discriminator with mask and alpha values. It is overall loss of our method. We add detection loss and global aligning loss. It is the results of our method, and ours category aware and B-box with aware, scale aware methods outperform significantly than other methods. And in addition, since the object category and object scale are complementary conditioning, So it can be seen that when the two conditionings are applied simultaneously, it achieved the highest performance. And it also showed good performance at Sin 10K to cityscapes. It is our ablation study. We hypothesized that just using larger dimensional features can improve the performance. So we conduct ablation studies on the precise impact of conditioning on the model predictions, and as shown in table 4. When Q is 1, alpha is always 1 during training, and as a result, but we observe that our conditioning improves the performance than larger dimensional of features. In conclusion, we demonstrate the distribution and discrepancy of FCOS backbone features with differing object scales, and we introduce a novel framework for adversarial feature alignment that conditions on object category and scale in a highly efficient manner. And we show the effectiveness of our proposed method through empirical evaluations on two widely used domain adaptation benchmarks, cityscape to foggy cityscapes and Zen10K to cityscapes. It's the end of our presentation, and thank you. Do you have any questions?
Okay, just a quick question.
Yeah.
Sorry, I mean, anyone? Okay, thanks.
Thank you.